Okay, Mrs. V, you know I've been here and I've been teaching for a while right next door to you. And I have a lot of these kids that cross over between physics and chemistry. And they talk a lot about this Sig Dig stuff. And I'm really not quite so sure what they're talking about. Can you fill me in?
Sure. Well, some people call them significant figures. So maybe you've heard of sig figs or significant figures?
Yep, I think that's how I learned it. That's why they laugh at me when I say sig figs.
Because for some reason, I just got in the habit of calling them Sig Digs for significant digits. And significant digits are always applicable when you take a measurement. So they have to do with measurements.
So only measurements.
Only measurements. So if I said there are 29 students in this room, well, that's not technically a measurement because there would be exactly 29 students. There would be no uncertainty. You would know for sure that there were 29 students. Or if I did a conversion, if I said there were 1,000 meters in a kilometer, that's an exact value. That's a for sure value. That's not truly a measurement. That's a conversion.
Okay, so like 1 inch equals 2.54 centimeters.
Would be a conversion.
So
you wouldn't do Sig Digs with that.
So we wouldn't consider.
Right.
Oh, okay.
But you would consider Sig Digs if you measured the length of your room.
Oh, yeah.
Or if you measured the mass of a sample of metal.
Okay.
Or if you measured the volume of some liquid in a graduated cylinder.
We do that a lot.
Okay. So in that case, you would want to use significant digits.
Okay. So now, how do I figure these Sig Digs out?
Significant digits are always all the parts of the measurement, all the digits that you know for sure, plus one estimated digit. For example, on a meter stick, on a typical meter stick, if we were to measure the width of a piece of paper, it would be about 21.54 centimeters. Now, there is a mark for the 0.5. So if you measured 21.5, there is a mark at exactly 21.5.
Okay.
So those are the digits you know for sure.
Right. And
then the last digit, the 4, would be your estimated digit.
Okay.
And so all 4 of those digits, 21.54, are Sig Digs. Because it's the digits you know for sure plus one estimated digit.
All right.
Now, the problem that students have is when they see a measurement that has been taken, and then they're trying to figure out how many Sig Digs that measurement has after someone else has taken that measurement. So that's why we have some rules to try and figure out, okay, so how many Sig Digs?
Okay. All right. So are these the rules here?
These are the rules.
Very good.
So the first rule says that any of the digits that are not 0 are always significant.
Okay.
So 56.1 has 3 Sig Digs. 45.879 has 5, and so on. 11, then number 11 would have 2 Sig Digs. Okay, so that's an easy rule.
Okay, and that's 11 as long as it's a measurement like centimeters.
Right.
But not if it's like students.
Correct.
Okay. And how many would it be, or we just don't talk about Sig Digs with counting numbers?
No.
We just don't?
No.
Okay.
No. So then the next rule has to do with zeros, and basically zeros are the problem. That's what students have trouble with, are figuring out zeros.
Okay.
The first couple rules are pretty simple about zeros. So the first rule for zeros says that if you have a 0 between 2 other significant digits or non-zero digits, those zeros are significant. If a 0 is trapped between 2 numbers that are not zeros, they're all significant. Like 3.108 has 4.
Okay.
4009 has 4 because there's a 4 on one end and a 9 on the other end. Does not matter how many zeros are in between.
Okay.
Okay. And then if we have 0.00109, the 109 are significant because the 0 is between the 1 and the 9. Now, you may be wondering about those zeros in front of the 1.
Yeah, like
we're
these,
gonna
these
talk,
in the front.
Yeah, those in front. We're going to talk about those later because that's actually another rule that applies too.
Okay.
Right now, we're just looking at zeros that are between two other Sig Digs.
Okay.
Okay?
Okay.
So that rule makes sense?
Yep, that does make sense. So if they're trapped, they're significant.
Trapped, they're significant.
Okay. Very good.
So let's go to rule 3. All final zeros after a decimal point are always Sig Digs. Final zeros after a decimal point.
Okay.
Okay? So if you have 4.320, that 0 is a final 0. It's after the decimal point that was a couple digits back.
Right
so that
there.
makes all 4 of those numbers Sig Digs.
Okay.
Then 1.00, again, those zeros are final zeros after a decimal point. So they are significant digits.
But isn't that 1.00 just the same number as 1? Isn't it just 1?
No, because that's a good question. If the value was just 1, that would mean that measurement was made to the nearest 1.
Okay.
This, with 0.00, indicates that the measurement was made to the nearest hundredth of perhaps centimeters, milliliters, meaning that it was 1 for sure. The tenths place, it was positive that it was a 0, and then the hundredths place, it was estimated that also was a 0.
Okay. So if it's a measurement, the 1 and the 1.00 are two different. They mean
Very
different
good.
things.
Exactly. Very good.
Okay.
Yeah. Now, the next rule for zeros, when you have zeros that are only placed there because they show us where the decimal point goes, they are called placeholders, and placeholders, although they are vitally important, they are not Sig Digs. For example, if you have a measurement like 400, that means that the measurement was made to the nearest 100.
Okay.
So in this case, we actually only estimated to the hundreds because all measurements have to have all the digits you know for sure and one estimated digit. And because there's only one digit there, I know that 4 in 400 is an estimated digit.
Okay. So it's about 400.
That's right. It's an estimate. It could have been 500. It could have been 300.
Okay. Okay.
But those zeros are important because, for example, let's say I owed you $400, and if I said, well, you know, placeholders aren't that important. How about if I just give you 4? You wouldn't like that.
Not at all.
No, right.
No.
So see, placeholders are important, but they're just not Sig Digs. All right, and then we have 0.0026. Those zeros are also placeholders because they show you which place the 2 and the 6 are in, where the measurement started. The 2 would be the digit that was known for sure. The 6 would be the estimated digit.
All right, all right.
And then in 70,000, again, all those zeros just tell you where the 7 is. So again, this is like the 400. The 7 is an estimate.
Okay. That's, wow.
Yeah.
See that, those zeros,
I know.
they seem very important to me, so I would initially call them
They are very important
but they're not significant.
They were not a part of the measurement.
Okay.
The measurement was only made to the 7. And again, they were estimating 70,000 or 60,000 or 80,000.
Okay.
Okay?
Very good.
Now, that brings us to the concept of, let's say, what if I have a number like 30 and I want to show that it has 2 Sig Digs?
Oh.
Because from what we just learned, if I wrote 30, that would only be 1 Sig Dig.
Right.
So the only way to show that that 0 is also significant in this case is to use scientific notation.
Because
whenever you write scientific notation, all digits in scientific notation are Sig Digs.
Okay.
And let's look at that second example because that's what I was talking about. When you have 3.0 times 10 to the second, that's the way that you can write 30 to show that you have 2 Sig Digs. Because 4.39 times 10 to the negative second would have 3 Sig Digs because all of those values are measurements that were made or the final estimated digit.
Okay.
Of course, if you took 4.39 times 10 to the negative second out of scientific notation, you would have 0.00439. And so again, those preceding zeros would not be Sig Digs.
Okay. This makes more sense to me.
Okay, good.